Hello everyone. In the previous lectures, we had seen how seismic survey can be carried out on the land, as well as we had seen little bit on how we energize to carry out the seismic survey on oceans, right. If you recollect, we had seen the survey can be classified into 4 separate headings. First is how do we carry out the survey to locate the short point and the detector points. Then we had seen how we energize the ground, then how we are going to pick up the signals. Lastly, we had seen how we are going to record the signals and how the signals recorded are also corrected, for especially for elevation and weathering. Now we have the data with us. The next part is how can we carry on with the interpretation of the data which we have collected. We have been also discussing that the signals which are generated or which are passing through the subsurface after energizing the ground may get refracted or reflected back to the surface. So, depending upon which data we are going to use, the seismic methods are classified as seismic refraction method and seismic reflection method. First, today in the next couple of lectures, let us look into seismic refraction method. As you can see in this simple animation, we have 4 geophones kept, and then we are giving a energy. The energy passes through the earth and which is getting refracted, and the signals have been received at the 4 geophones, right, at different times, and we know the distances of the geophone from the short point, and we have the corresponding first arrivals, right. First arrivals at geophone number 1, 2, 3, 4. We have the arrivals at all the geophones. With the help of this, we can determine the thickness of the first layer. So, this is in brief about the seismic refraction method. That means, what did we do? We had energized the ground and we have arranged couple of geophones. In this diagram, we have used 4 geophones, and we know the distances of these geophones from the short point, and we also have the arrival times at all these geophones, right. How did we get the arrival time? Because the arrival times are recorded on the seismograph, right. We have used 4 channel seismograph. All these 4 channels are recorded. Now we have the arrival time and the distances of these geophones from the short point. That means the location where we have energized the ground. Using this, we can determine the thickness of the first layer, that is in this diagram it is represented as ZR, right. So, this is in brief about the seismic refraction method. How the seismic energy is getting refracted back to the surface, right. Seismic energy returns to the surface after traveling through the formation along the refracted ray path, right. It also gets back to the geophones by reflection, but here in this lecture or in the next couple of lectures, as I told you, we are going to focus on seismic refraction, right. How it is getting refracted? Let us see. This is the source, right. We can use explosives, or we would have given a hammer blow as we had seen on the previous page. The signals are getting in and they are refracted back to the surface, which are sensed by the geophones after refraction. Why do they get refracted back to the surface? They get refracted back to the surface because the signals may go and meet the interface, that is, this is first layer, second layer, third layer. Corresponding velocities are V1, V2 and V3. right. So, let us take up this particular ray. This seismic wave meets the interface at critical angle. When it meets at critical angle, just like law of light, right, here as it meets the interface at critical angle, it is totally and internally get refracted. So, it travels at the surface, just beneath the surface, but with the velocity of v2. And as it travels here, the noise shock created by this is also heard by the geophones, right. These are known as head waves. So, head waves are heard by the geophones, right. So, these head waves are reaching the geophone, right, and these are the refracted signals, because the shock wave has met the interface at the critical angle. So, it got internally refracted, and the refracted signals are also reaching the surface, which is known as head waves, because the geophone which are kept at the surface is able to hear the noise generated by this critically refracted wave, right. Similarly, some signals get refracted and meets the next layer at critical angle, right. Here at critical angle it meets the next layer. So, in the second interface it is getting critically refracted, that means total internal refraction, and this signal is also heard by the geophone at the ground surface. So, head waves are created in all the layers. Since we are going to analyze only the refracted signals, this method is known as seismic refraction method. So, actually what we do, we carry out survey at the surface, right, by energizing the ground. These are the array of geophones, right, and the signals which are getting in gets totally internally refracted and which are heard. So, these are the refracted signals. At the same time, we may also have the reflected signals reaching the surface, as you see here, right. But in this method, we are going to look into the refracted signals only, because here the seismic wave meets this. If it is not at critical angle, it is completely getting reflected. If it meets at critical angle, it is totally internally refracted. If it meets at an angle greater than that, it is internally refracted and passes through the next layer, isn't it? So, this is what is happening. So, you have both reflected as well as refracted rays reaching the surface, but now we are going to focus on looking into the refracted signals. Now, let us take an example in which there is a short point, all of them are geophones. Geophones are arranged at the surface as you see here, right, and corresponding records are indicated here in the seismogram, right. That means the seismograph, which is an instrument to capture and record the ground motion, that is what it has done, and the record it has created is known as seismogram. So, here is the first geophone. What is this axis? This axis is the distance, ground distance, that is this, right. For example, this geophone record is here, next geophone's record is here, right. This is time, right. So, in the first geophone, after the shot is fired, you have some signal, then there is some lull period, not much of a signal, then there is a next major signal. Here too, first and next major arrival. For simplicity, we are just showing or seeing only the major shocks, right. In fact, in between you will have something like this, right. First vibration, then it dies down, then the next one, then the next one. So, this is how it will be, but we are only looking into some major, first major shocks, again major shock, that alone has been indicated in the seismogram for simplicity here, right. Now, if you look at the first geophone which is located here, this geophone primarily receives the direct rays, right. The direct rays are in fact the first signal it receives. Okay. So, the geophone number 1 now received the direct rays first. Then after some time it receives this reflected signal. This is a reflected ray, isn't it? So, this reflected signal is also reaching the geophone number 1. Whereas, some geophones beyond certain distance also gets the refracted signals. These are all head waves due to this. Okay. Thus, when you install geophones, geophone picks 3 different signals. One is the surface, which are known as direct rays, then refracted and also reflected signals. But we are able to differentiate that, right, from the seismogram. How? That is what we are going to see here. Now, imagine that, as I told you, in the first receiver or geophone number 1, the first arrival is the direct ray, okay, because this is reaching faster. Since the geophone is located very close to the source, first receiver 1, 2, 3, 4 and so on, it receives the direct signal or direct seismic waves first. Okay. But, right, as the refracted ray travel down the interface, it will not return to the surface up to certain distance. What do we mean by that? That means, for refracted signals to reach the surface, the seismic wave should meet this at critical angle, isn't it? Only then it gets internally refracted, total internal refraction, and the waves are traveling at the velocity of the second layer, which can be heard by the geophones. So, in order to have this signal reaching the surface, it has to meet at critical angle, right. To get critical angle, you need to have some distance from the short point to the receivers. So, that is what I am saying, indicating here. In this is the geophone, first geophone which receives the refracted signal. That means number 4. For simplicity, this is number 4, which means for this configuration, geophone number 1, 2, 3 will not receive refracted signals because they are very close to the short point, right. It so happens the critical angle is, because that is dependent on the thickness of the layer. The thickness of the layer is such that the shock waves could meet the first interface for internal refraction only at this location. That means, only at this point it is able to meet the interface at critical angle. Is that clear? So, since it is meeting only at this place at critical angle, this is the first geophone to receive or hear the refracted signals. Okay. So, this distance in seismology or in seismic methods we call as critical distance. Okay. What is the critical distance? This is a plot of distance versus time, right? Distance versus time, x versus t. Only after some distance, that distance is known as critical distance, right? That means only after this distance we are able to get the refracted signals. Okay, until that we will not have refracted signals. That means up to this distance the geophones are not receiving any refracted signals. Okay. So, if you look at the next case, right, which is beyond some distance, right, beyond some distance, right, let us say that is this distance, the refracted rays are overtaking the direct rays. That means up to this distance the geophones are receiving the signals. That is what, which signal? This direct ray. Direct ray passes very close to the surface, are received by all the geophones. But what happens beyond certain distance, right? This is the direct ray. Sorry, this is the direct ray. The direct ray are overtaken by the refracted signals. That is why the time taken for the refracted signal to reach these geophones are comparatively lesser than that of the direct rays. Okay. So, what is happening beyond certain distance is the signals which are reaching here, part of the refracted signals are traveling, are reaching this place. This is the ray path, and most of the distance it is covering with a velocity v2, right. Usually v2 will be greater than v1, v2 will be greater than v1. It is generally that will be the case. Why? Because during sedimentation process, in general layers at greater depths are more compacted. So, they have more density, more elastic constants, right, high rigidity modulus and bulk modulus, due to which in general layers below will have higher velocity, seismic velocity than the layers which are immediately above them. There can be some exceptions, right, but in general this will be the trend. So, the seismic signals have travelled part of the distance. So, this is the path it has taken. Part of the distance is covered with high velocity, right, because this shock wave has travelled at layer 2, due to which beyond certain distance the refracted signals are reaching faster. So, correspondingly we can have a look at the seismogram here. For this particular geophone, let us take this geophone. So, this is the first arrival in the geophone. First arrival in the geophone will be due to refraction. Then there is next major arrival. That arrival will be from where? From direct. This is refraction, this is direct. Then there is one more arrival, that will be reflection. Okay. So, this diagram helps us to understand the geometry of seismic waves, right. Then velocity of the reflected ray and the refracted ray is actually same at the critical distance. right. So, what is critical distance? Critical distance is the distance at which we are going to start getting the refracted signals. Where is it? Now, this is the critical distance. At the critical distance, the geophone is able to hear the refracted signal as well as the reflected signal. Both are one and the same, they arrive at the same time. So, at the critical distance. Now, let us have a look into reflected signals, right. So, if you take the first geophone, this is the reflected ray path. If you take the second geophone, the reflected signals are traveling and reaching this. Third one is like this. This is the fourth one we have already drawn. Fifth one is here. Sixth one is something like this. Seventh one like this, right. And if you take the arrival times of all the reflected signals and plot on that, but this plot is known as time distance plot. If you plot, they will all follow this curve. This curve is due to reflected signal, right. Reflected signal is always slower because if you in comparison with direct ray, direct and reflected ray in layer 1 travel at the same velocity, but the direct rays are able to reach, let us say, this geophone by traveling this much of distance. To reach the same geophone, reflected signal takes a long route. So, they are taking much more time. Direct wave has reached at this time, the reflected ray reaches at this time. Similarly, refracted signal reaches at the same time because this is the first geophone, that is critical distance. At the critical distance, we have seen the velocity or arrival time of reflected and the refracted ray will be the same. Okay. Then beyond that, the reflected signal takes more time to reach the surface because it has to travel greater distance, whereas direct is reaching faster than reflected. Refracted signal are reaching much more faster than the direct. That is what we could observe here. If you take this location, refracted is first, next is the direct, third is the reflected signal, right. Suppose if I want to demarcate, this is the direct, this is refracted, the third is reflection. Okay, is it clear now? So, from this diagram, we have understood the geometry of the direct, reflected and refracted ray paths. It is evident beyond certain distance, the geophones are receiving refracted signals faster than even direct as well as the reflected. And the next important aspect is reflected signals are always slower. Why? Because reflected signal to reach a geophone which is located at, let us say, 200 meters, direct seismic wave just travels 200 meters, whereas the reflected signal takes a longer route, that too the length of the path it has taken depends on the thickness of the formation. If thickness is more, reflected signal takes more time. The next important point, third important point here is refracted signals are the ones that is received first by the geophones beyond certain distance. That distance is known as crossover distance. Okay. So, we have now understood how the seismic waves are traveling below the surface of the earth, that is direct, refraction, reflection, and we have also seen two important things. One is known as critical distance. Critical distance is the distance beyond which only the geophones will receive refracted signals. Then we have seen one more thing which is known as crossover distance. Crossover distance is the distance at which reflected signals as well as direct signals are overtaken by the refracted signals, right. Very simply, refraction overtakes the direct rays. That is what is known as crossover distance. Right. After having understood this, let us now see how we can determine the thicknesses of layers by seismic refraction method. As we have seen on the previous page, always we are looking into some simple cases. We plot the distance versus time. This plot is known as hodograph or simply time distance plot, right? Time distance plot. How did we plot this time distance? Just like what on the previous page. This is the time distance plot. How did we plot this? By noting down the arrival times from the seismograms of all the geophones. Now we have used about 20 geophones. They are at different distances. What are the arrival times? That especially the first major arrival, second major arrival, third major arrival, right. This is what we have plotted here. But here, since we are going to focus ourselves only on the refracted methods, we are plotting the arrival times of direct and the refracted signals. Now, we can understand the location of the bedding plane or discontinuity in the subsurface. This is the surface of the earth. This is layer 1, layer 2. The discontinuity in the subsurface or the subsurface formation is indicated by the break in the slope of the line, right, indicated by the break in the time distance curve. Actually, we have two segments of straight lines. The first segment is from layer 1, second segment is from layer 2, right. And since we have now plotted the time distance plot, it gives also the velocity, right, because we have distance travelled and the corresponding time taken. So, distance travelled and the time taken is nothing but velocity. In other words, the inverse of the slope of the line or slope of this segment gives the velocity, right. So, the velocities of layer 1 and layer 2 thus can be determined by us from this time distance plot, okay, because we have the distance travelled and the time taken, that is nothing but the velocity, right. And we already have learnt about crossover distance, right. We know what is crossover distance already. What is crossover distance? Crossover distance is the distance at which the velocity of direct rays or the time of arrival of direct rays are overtaken by the refracted signals, right. And the extrapolation, we will learn one more thing here now. The extrapolation of the second layer, right, so as to meet the y-axis, it meets the time axis. That point is known as intercept time, right. So, Ti, which is known as intercept time, and from the geometry of the wave paths, right, From the geometry of wave paths, we have already seen this is the surface, ground surface, this is the first interface, short point, detectors, that is geophones, right. Beyond certain distance, refraction takes place. So, these geophones receive the refracted signals, right. From the geometry of the wave path, right, we can determine the depth to the second layer, or in other words, we can determine the thickness of the first layer, right. How? By using the crossover distance or by using the intercept time. That means, we can either use the crossover distance or the intercept time to determine the thickness of the first layer. That means, researchers have worked out a simple relation considering the geometry of the wave path, right. So, here is a simple two layer case, as we have seen on the previous slide. There are two layers. This is the path taken by the refracted signals. We have the crossover distance and the intercept time, and now using the crossover distance, the thickness of the first layer can be estimated using this equation, right. And what are they? This is crossover distance. V1 and V2 are the velocities. How we are going to estimate V1? V1 is nothing but the distance travelled and the corresponding time. In other words, inverse of the slope of this line is the velocity, that is V1. Distance travelled and the time taken, this is V2. Okay. So, thickness of the first layer Z is equivalent to crossover distance divided by 2 within square root, right, within square root V2 minus V1 and V2 plus V1. So, using this relationship, we can determine the crossover distance, right. Why it is getting internally refracted? Because at this location it meets at critical angle, right, just like the law of light. Now, there is also another way to calculate the distance, as we had seen on the previous slide. That means, the relationship has been worked out with respect to crossover distance as well as the intercept time, right. So, using intercept time, the depth to the first layer or thickness of the first layer can be estimated using this relationship. V1 multiplied by Ti, Ti is the intercept time, Ti is the intercept time. We have already seen what is V1 and V2. V1 is the velocity of the first layer, that is the top layer. V2 is the velocity of the second layer. So, thus, without actually drilling, we are able to understand the thickness of the layer by carrying out a simple seismic survey. Even a hammer blow is sufficient, right, as we had seen in the first animation page, right. We are able to determine the thickness of the layer, right. So, we have understood how we can determine the thickness of the layer for a two layer case.